Hey there, we're going to talk about integration with u-Substitution. And if you are a random passerby on the internet and you want to print a sheet to kind of follow along and take notes, you can go to this bit.ly link right here. Make sure to use all lowercase letters because the capital u-sub was already taken. So let's talk about u-Substitution. And one thing to know about u-Substitution is that it is the process of undoing the chain rule. And so we are doing the chain rule in reverse here. So I guess if we're going to undo the chain rule, we need to refresh ourselves on how the chain rule works. And so I have two very, what I think should be easy derivatives up here. The derivative of this first function, we bring the 4 down, we will leave that x squared plus 3 to the alone, raise that to the third power after subtracting, and then times the derivative of the inside. Number 2, the outside function is tangent x. The interior is natural log of x. So we're going to ignore the natural log and we will differentiate the tangent first. That'll be secant squared. We will leave its argument alone. So the natural log of x is left alone. And then we would multiply by 1 over x. And there is a very quick review of the chain rule. And if we're going to do the chain rule in reverse, then what we're going to need to be able to do is identify some inside function, no different than when you were doing the chain rule. You identify an inside, which you ignore, and then in the end, you multiply by the inside's derivative. So we want to identify some inside function, and in these two cases, the inside function, the inside function is here and here. That is inside the other functions of secant squared and 4 times stuff cubed. And then you also want to, while you're identifying the inside function, you want to simultaneously be looking for the derivative of that inside function. So here, and again, we're going from right to left with u-Substitution. So I'm going to give you something that looks like these blue answers, and we have to turn it into the original problem over here. And in doing so, you will look for an inside function and its derivative. And that's the indication that what we're looking at is the end result of a chain rule derivative. So let's look at a couple of examples. And I have 6 total. I'm not going to work them all out in great detail because I have already tried that once and the video ended up being close to 30 minutes, which is entirely overkill. So let's look at this first one. I want to find the antiderivative of this thing. It's not a power rule and it's not recognition. You always want to consider algebraic options to make the antiderivative easier. The only way you can turn this into a power rule antiderivative is if you fully expanded x squared plus 7 to the 6th power, which would obviously be way too cumbersome. And so what I'm going to now do is I'm looking for an inside function that has something else happening to it. And I see that with x squared plus 7 because all of that is being raised to the 6th power. So I notice that. And I also noticed at the same time that the derivative of that inside is right here. So the inside's derivative is also evident in the antiderivative or the integrand here. And the reason we call it u-Substitution is if you want to go through and do this very formally and pretty, you would actually substitute out the inside and you would consider the inside to be some representation of a function u. So I'm letting u be x squared plus 7. And then I also notice the derivative of that u is right here with the 2x. Now, after you identify a u, so I'm choosing u to be x squared plus 7. What I will do next is I completely ignore the original problem. I'm not looking at my problem one bit, and I'm just channeling my old calculus from like the beginning of the year. I'm going to find the derivative of that u. So u prime would be 2x. Except I'm not going to call it u prime because I'm a huge fan of Leibniz notation. I'm going to call that the derivative of u, du, dx. And then I'm going to do something really unique here. I can multiply both sides of this by dx. And when I do that, the dx's over here will divide out, leaving you with only the du on the left side. And I'm left with du is equal to 2x dx. Now, this may be the only time I actually do du dx and then show the multiplication to move the dx over. What I will do from now on is I will skip straight from u equals x squared plus 7 straight to du is 2x dx. And in u-Substitution, the most important thing you have to identify is that du. You want to make sure that whatever the derivative of your u is evident in the problem, and it is right here. So the first thing I'm going to substitute is the du. So I'm going to take 2x dx. I will replace that with a du. So over here, I'm going to rewrite my antiderivative. 2x dx is now a du. And notice I left a lot of empty space between the squiggle s and the du because I want to leave room for everything else. Then I look over here, I see x squared plus 7, all to the 6. but x squared plus 7 and u are the same thing. So instead of x squared plus 7 to the 6, that becomes u to the 6. And I have now completed the u substitution step. Now notice that did not give me the answer to the antiderivative. U substitution does not accomplish the integration. What it does is it takes an ugly antiderivative, a lot of stuff going on over here, and it turns it into something nicer right here. I went from this ugly product to just u to the 6th du. And again, for a minute, I can ignore the original problem and I can just do the antiderivative of this. That would be u to the 7th divided by 7. Or you could say 1/7 u to the 7th plus c. There's the antiderivative, except you don't want to leave it in terms of u. U is just kind of a intermediate step to make things a little bit easier to digest. You're not done until you have an answer in terms of x. So now I simply take the x squared plus 7, I put it back in the place of that u, x squared plus 7, all to the 7th, divided by 7, plus c. That's a lot of 7s. And there is your final answer. So there is a u substitution problem shown in great detail. And I'll do one more, and then I may kind of jump through some of the others a little bit more quickly. If I can, I'm going to keep throwing a few more curveballs here. So here I'm looking for an inside and its derivative, and I think that's kind of easy to see here because I see an x cubed, and I know the derivative of x cubed is 3x squared dx. And I have that right here. I have my 3x squared and the dx. Together, those two things are completing the du requirement. And at that point, I can go on and start substituting. So 3x squared dx, those are taken out of the problem. They're gone, and they're replaced with a du. Now look at everything else. Once you start making the change from x's to u's, everything that was x needs to be converted. This is going to be kind of nice because x cubed is u. So that's going to be cosine of u. And the objective of u substitution is not to give you the answer, it's to give you a nicer antiderivative that you can wrap your head around. And the antiderivative of cosine u, that is recognition. You should recognize that as the derivative of sine. So the antiderivative of cosine is sine of u. And final step, we will replace the u with an x cubed. So there is the answer for this problem. So that brings us to number 3. This is an uglier one. Oh, a blank up here. The most important part of u substitution, I mentioned this earlier, you absolutely must identify and substitute the du first. There are times where if you substitute the u in before the du, you can mess up the problem. So always make sure that du is there and ready to be plugged in before you do anything else. And if your du is not there, that means you either chose the wrong thing for u, you made some other mistake, or maybe it's not even a u substitution problem. So let's go on with number 3. We have secant squared over tangent. And remember, you're looking for something and its derivative. And hopefully this one is staring at you right in the face. You should recognize secant squared as the derivative of tangent, which means I'm going to let u be the tangent because I see its derivative already. The derivative of tangent is secant squared x dx. And in my substitution, I like to identify the du, which I have here, the secant squared x and the dx together are completing that du requirement. And so as I'm substituting, I have a fraction here. I'm just going to go ahead and put a fraction bar just to remind myself that there is a fraction because some people will mess this up if you don't do that. Secant squared x dx come out to form the du. Now the numerator of secant squared is part of the du, so the numerator disappeared. I like to put a 1 there to hold the place. Tangent x is my u, and so now I'm left with 1 over u, which again is recognition. You should see that and just know that that is the derivative of the natural log of u. And then we will plug our tangent x back in, plus c. Cool. And so number 4, let's think about what u should be. And for number 4, I don't see the parentheses that I kind of like to see for u substitution, but I do see something kind of ugly here. I see a 1 plus x squared under a square root when I would prefer to have just like the square root of x. I don't like that 1 plus x squared. So I'm going to see what happens if I let u equal 1 plus x squared. And if I do that, I end up with du being, and here's where you have to be careful. Don't look in your problem and try to identify what du might be. When you're finding out what du is, you're going back to what we've been doing for months now. The derivative of 1 plus x squared is 2x. Don't try to force the du to be what you want it to be. You're simply differentiating your choice for you. And before I do anything else in this problem, I need to make sure that I have 2x dx ready to use in my problem. So now I'm going back up to the original, which I forgot what it looks like. And oh, there it is. And I look for 2x dx, and we have a bit of a problem because I have the x, I have the dx, but I'm missing the 2. If all you're missing is a constant multiple of whatever your du is, that can be fixed. If you're missing x's, that's much more difficult to remedy. And usually I'll just kind of start over. If I get to a situation where I'm missing x's, I'll oftentimes just start over. In this case, if you're missing a 2, that's not a big deal, because if all you're doing is missing a constant, you can fix that by just putting a constant in here. Hey, I would rather there be a 2, so let's just put a 2. And you're thinking, well, you can't just change the problem to what you want it to be. And you're kind of right, but sometimes you can, as long as you can undo that change that you just created. So when I put that 2 there to complete my du, I multiply by 2. So if I multiply by 2, I need to undo that by dividing by 2. So what I'm actually going to do is I'm going to multiply by 2 and divide by 2 simultaneously. So it looks different, but it's still a 1, except instead of dividing by 2 on the inside like this, I'm going to multiply by 2 inside so that I see my du. I'm going to divide by 2 by multiplying the entire integral by a 1/2. And what we're doing there is we're taking advantage of the property of integrals that says if you have a constant times your integrand like this, you can take that constant out of the integral. And that's essentially what I did with that division of 2 that I originally had inside the integral. I'm just taking that 1/2 and putting it outside instead of inside. And by doing that, I've accounted for the change that I created in order to complete my du. And now I'm ready to continue with my substitution. So with my substitution, the 2x dx comes out to form a du. The square root of 1 plus x squared now becomes the square root of u. And you have to remember that if you put a constant in, like I did that too, I had to multiply by 1/2. That 1/2 is now a permanent fixture of the problem. The 2 is actually part of the du. So the 2 got substituted out for the du, but the 1/2 does not get substituted away. It's there forever. And then the antiderivative of the square root of u, you would need to think of that as u to the 1/2. And now we can power rule u to the 1/2. 1/2 plus 1 is 3/2. Divide by 3/2 is the same as times 2/3 plus a c. And then we substitute the 1 plus x squared back in for the u. And I am going to divide those 2's out. So I have 1/3 now, and then u, which is 1 plus x squared, to the 3/2 plus c. Okay, so let's look at number 5 very quickly. I'm not going to work this one out in detail. I will show you the answer here in a few seconds. But if you want to pause the video and give this one a shot, you've had maybe a second to think about it now. I'm going to go ahead and tell you that we will choose u to be x to the 4th. We'll choose u to be x to the 4th, and that's pretty common. If you have an exponential function with an ugly exponent, you very frequently will let u be that ugly exponent, and then you find the du and see if it works out. And in about 2 seconds, you will see the answer to this one. And here's your final answer. So we again had a situation where my du was 4x cubed, and I was missing the 4. So I put a 4 and a 1/4. After substitution, it ends up being very nice. The antiderivative of e to the u is e to the u. Replace the u with x to the 4th, and don't forget the 1/4 in front comes along for the ride. So number 6, the natural log of x all divided by x. And this one I'm going to make 1 point, and then I'll show you the correct way to do it. So what I'm about to show you is not going to work, but a lot of people will look at this one and you don't see the obvious parentheses indicating an inside. You don't see square roots. And so some people are thinking, well, there's an x in the denominator, and we chose the denominator for u earlier. There's also an x inside the natural log function. So maybe u is equal to x. And let's see what happens if you let u equal x. Well, the derivative of x is just 1, but I'm going to go ahead and multiply by the dx also. The dx is part of the du, so put it there. And so 1 dx, well, 1 dx is just dx. And because I see the du there, du is dx, we can theoretically proceed with the substitution. I take the dx out. I replace it with a du because du and dx are equal. Then I notice that I still have x's left over, but x is the same thing as u. So that will become the natural log of u divided by u. And there is the new integrand after substituting everything out. And you'll notice that it didn't help one bit. The objective of u-Substitution is to create a new antiderivative that is nicer and easier to process than the first. And these first 5 examples all did that. After substituting, we ended up with a much nicer antiderivative. This is the exact same function. Nothing changed except the x's are now u's. So you will never, ever, ever, ever do the substitution u equals x. It doesn't help you. It gets you nowhere unless you just don't like the appearance of the letter x. So always choose something a little bit uglier than just an x. And in this one, the u is actually going to be the natural log of x. And so I'm going to go ahead and give you that hint, and I'm about to pause this and finish working it out. And if you want to work it out and see if you did okay, you can pause the video and work it out on your own. And here's my final answer. The derivative of the natural log of x is 1 over x. That was already in the problem. You can barely tell that I did write a 1 there just so I can see the 1 over x. That wasn't really necessary. But that denominator of x actually ended up being part of the dx. That should be a du, not a dx. Ended up being part of the du right here. And kind of like I did before, I still did my substitution as a fraction since the denominator is part of the du. Then I just put a 1 to hold the place of the denominator, which ends up being just the antiderivative of u, which is u squared over 2, and then substitute the natural log of x back in. So a few pointers as you are looking through substitution problems, places where you can look for a u. So if you're having a hard time deciding what to choose for u, there are in my opinion, 4 main places where you can look for a u, and I'm going to just unveil all these and talk about them, and then I'll go back and I'll give you some written examples of antiderivatives that fit each of these categories. So the first, probably the most obvious one, is going to look inside parentheses. Just make sure that there is some operation being performed on those parentheses. And that's kind of like what the very first example was, where we had like a polynomial to the 5th power or something like that. Number 2, if you have a radical, you want to look under the radical, which I guess more mathematically, I should say the argument of the radical, the radicand. But anything that's inside a radical, if it's not just a nice clean x, you often will let that radicand be the u. You can also look in the exponent of exponential functions when you have an ugly exponent, and that was the e to the x to the 4th example we just had a minute ago. It was an uglier exponent than just an x, so we let u be the ugly exponent. And then if you have a fraction with variables in the denominator, you very frequently will choose either the entire denominator or a part of the denominator to serve as the u. And many times in these situations, the du is either the entire numerator or part of the numerator or something along those lines. And I'm going to pause this and I'm going to write a few examples showing you antiderivatives that feature each of these 4 situations. Okay, so here's some examples of each of them. And so if you're looking for the parentheses indicator, that's, in my opinion, the most obvious. Here we have things in parentheses, and something is happening to those parentheses. It's not just x times x squared plus 1. It's x squared plus 1 all to the 7th. It's that other operator on the parentheses that makes me think I'm going to let u be x squared plus 1. Similarly, over here, inside the sign, I see a natural log of x. Instead of just sine x, it's sine natural log x. I'm going to let u be that natural log of x. Down here, the radicals, which is kind of in the same category as parentheses, because you can rewrite any radical like this as, in this case, it'd be the quantity of x cubed plus 7 all to the 1/2 power, which then puts it in the parentheses category. But I did list this as a separate thing to look for. So I'll let u be x cubed plus 7. And the important thing is the derivative of that is visible. In sine of natural log of x, the derivative of natural log of x is 1 over x. The derivative of x squared is 2x, and we can fix the missing 2, so the 2 is not a problem. The key is that we had the correct x in that problem. Down here in the exponent of an exponential function, instead of just sine of x, it's sine of cosine x, and the derivative of cosine is negative sine, and I have the sine x, the negative is not a problem. I can put a -1 here and offset that with a, I guess to be consistent, I'll put 1 over -1, the reciprocal. That's really just a -1 on the outside. And then in the denominator, if I let u be x to the fourth plus 1, I can put a 4 in that numerator, and 4x cubed would be the derivative of the denominator. I like that. I would have to put a 1/4 out here. But sometimes you don't choose the entire denominator. So this one's very similar, except now, instead of choosing the entire denominator as u, I'm only choosing that piece that's in the parentheses, which again goes back to the parentheses indicator on number 1 up there. And just like the other one, I just need to slap a 4 up here and a 1/4. And then I'm at 20 minutes. And so, yeah, so I think I had to pause and think for a minute. I think that's a lot to digest. I did have one more thing to cover. I think I may make this a separate video. I'm going to go ahead and cut this one off here because 20 minutes is already way too long. And we will polish the rest of this up in a second lesson. And hopefully these first few examples made some sense. Dip your toes in the water of u-substitution.